So this is the second.
We do see a lot of different cultures.
Oh, this is very varied, I would say. I have seen calling for agents, and also doctors who are on with agents. And I've also seen people who are
It's really good to see you. Nice to meet you. How was your trip?
Yeah, it was good. There was actually a small I had to make because it routed all the way south for us to fly to Houston.
Hey, Kevin. Can I?
So that was scary, but like everything else was fine.
But you made the connection, obviously, or figured something out.
Yes. Like,
Oh my goodness. 5 minutes in an airport is. The one in Atlanta, I heard a joke that the designers were like, what if we had them run a 5K in between their flights? That's what it feels.
Yeah, I know.
Make a couple of quick announcements about the schedule getting shuffled. Yeah.
Hi, Kyle. Good to meet you.
Nice to meet you.
Also, if there's just doing a conference working with me, yes. Yes, but it's a very common. My fourth year now.
Okay. What are you up to?
Basically, there's been like a lot of like simulation basic for stuff. I've only downloaded now.
Looks like we're losing people here. Maybe I'll just make sure that the microphones are on and working. Oh no, we've lost our AV team. Are the microphones projecting to the back? No. Yeah.
I was just talking with him.
Oh, okay. Where'd you go? Yeah.
It's just very complicated.
All right. Are the microphones projecting to the back? Can folks hear me okay? Or okay, great. Before we get started, just one announcement this morning, and that is that the schedule for this morning has shuffled around a little bit. We had one speaker who wasn't able to make it, so we adjusted things so that all of the formal talks this morning and the poster pops will be before the coffee break. All right, so take a look on the Slack. There's also an updated schedule on the big poster out by the door if you need to know sort of what the timing of things are. Okay? All right, Alberto, I'll hand it over to you.
Okay, good morning, everybody. So I will chair the session, and we will start right away with an invited talk by Jesse Lee from University of Texas, Austin. Jesse?
Thank you.
Is this working? Hello, can you hear me? Okay. Okay, great. Yeah, thank you so much for the invitation. So I'm from UT Austin and also part of the Cosmic AI Institute. I'm more of an NLP person, so I don't know too much about astronomy, but I will promise that one of the topics will be very related to astronomy. Okay, so today I'm going to say a little bit about evaluation in today's LLM and NLP world. It's a very complex and big topic, but hopefully we will present 3 case studies that kind of gives you an idea what's going on. So I want to start with one of the biggest benchmarks and probably the most famous one. This is multiple choice question answering at the graduate student level. So this was 2025. Back then, the LLMs are kind of getting these numbers of accuracies. And within a year, look at how much the numbers have climbed. So it gives you this idea that large language models are really advancing a lot in their capabilities. But when you think about it, we can see these numbers because these are numbers that are measurable. These are closed-ended tests where you can actually do a multiple choice and measure accuracy. But actually, most of the things that we ask language models are more open-ended. Right, so these are just a picture of the kinds of open-ended questions or queries that the language models get. So you have creative content generation, you have like a lot of like open-ended analytical questions, style analysis, they're seeking alternative perspectives and asking for decision support and so on and so forth. So it's really vast. And I guess related to science, there has been this new wave of AI for science, where you have a pipeline. So this is the AI scientist paper that made a big splash, where you have this like more agentic workflow that an AI is taking scientific ideation all the way through execution and paper reviewing as the full pipeline. And here is Denario, an agent out of the Flatiron Institute, where you have, again, a pipeline where you have from ideation to execution and analysis and paper review. And this makes you wonder, how do we even tell whether the language model is doing anything of like close to a good job? So this really goes to the field of evaluation, and I want to just give you a really brief overview how that looked like hand in hand with the advancement in technology in NLP. So here is like a very, very brief history of how things evolved. So back in the 1950s to 1980s, we have mostly rule-based systems where you have handcrafted linguistic rules and expert knowledge bases. And on the evaluation side, people were mostly doing error checks, analysis, and very domain-specific error metrics. So the statistical revolution happened decades later, where we actually had corpus-based probabilistic methods. And this is where the first machine translation systems came, and where we started developing more standardized metrics. For example, for machine translation, we had this famous comparison between a reference and the translation. It's called BLUE. In the 2010s, we had the deep learning era. So this is where neural networks were heavily built. Word representations like vector space representations for words were built, and we have sequence-to-sequence models for things like translation. And this is where more kind of standardized benchmarking actually started, where we had things like SQuAD or GLUE for kind of linguistics and also question answering, and we have more distributional-based metrics. And now, fast forward to the large language model era. Of course, this is where the large-scale transformer systems came, where we had more generalist question and answering systems that you see today. And for evaluation, we have also advanced to human preferences and really large-scale holistic benchmarks where LLMs are becoming judges. And we have also verifiable rewards where you get verifiable answers that you can then feed back into your model training. So if we center on evaluation, I would like to say that this is a key piece of the entire development cycle of large language models. So you start from a model, you do your evaluation, and you perform some error analysis. So for example, if this was a math domain, you can say, okay, the models aren't doing that well in math, so what do we do? What can happen is you can continue to get some data in this domain to do some curation or synthesize your data such that you can get this data to train the language model again. Okay, so the type of errors that you see with language models output becomes a source for how you source the training data, and then you kind of feed that back into the language model training, and then you do this evaluation loop again. But what I wanted to talk about is how about very open-ended tasks in science writing, or something like very difficult to even define, things like creativity. So what I want to briefly talk about today are three kind of thrusts that we have recently developed to give you a high-level picture of what's concretely being done. And I will start with how do we evaluate scientific visualization when the model is queried to generate one? And this is our recent work, AstroVisBench. After that, I will move on to kind of how do we measure associative creativity. So this is kind of more in the concept connection domain. And then I will end with a high-level picture of an agent that for evaluation, when you do not know what kind of criteria that the model needs to be evaluated on in the first place. Okay, so for AstroVisBench, let's imagine this scenario. Let's say you're an astronomer, you want to kind of plot something, and you're interacting with a language model. The language model will generate some code to do this. Once it generates the code, you can execute the code so that it comes with this visualization. Now, the question is, how do you know this visualization is good or bad? So the questions we're trying to ask is how adept are language models in reasoning through this kind of astronomy-related task? Can it use tools, APIs, and so on? And also, can the model even understand what is scientific utility in the figures that they're generating? And our idea is if we can find tasks with ground truth code and output and visualization, then we can reverse engineer and compare the model's capabilities. So AstroVisBench is a code and visualization benchmark we developed. It's derived from Astro-related Jupyter notebooks, and it contains 864 data processing and visualization tasks. So the pipeline goes like this. We have Jupyter notebooks. It has some context, and it has a query in natural language. The target is these visualizations that are associated with each notebook. And that's also the end product that we really want to evaluate the models on. What we do is separate the notebook into three types of code chunks. Setup code, so for example, define variables and global variables, and how do you import packages. We have processing code, where we process the data such that we get the kind of data ready for visualization. And finally, we have visualization code, that is how the visualization was actually parameterized and performed. We focus on these two types of code. So we have generated code and we have visualization. Now, the idea is we can perform the inspection on the variables that got generated, and also we can judge the kind of visualization that was derived when we execute the generated code. For data sourcing, we actually used Data Lab notebooks from NORA Labs, as well as the Space Telescope notebooks. So yeah, it's really nice to be here and talk about this. And we have a bunch of very different kind of angles of analysis and applications with different types of astronomy APIs involved. Okay, so taking a quick look at the processing tasks. So these are a bit simpler than visualization because you are looking at objects created by the model, and you can execute that in code and you can compare. So we source the queries by extracting and and synthesizing the query from the notebooks to be more full-fledged. And what we can do is, when we have some ground truth code, we can execute it and understand what are the key variables and their values. Now, with the generated code, we can also execute it and get the key variables and their values. And then we can just compare the key values, whether they are the same. So this is a little bit more straightforward, but I guess the highlight is how do we evaluate the visualizations that was generated. So basically, we compare the visualization from the ground truth code execution and the visualization from generated code execution. We used a language model as a judge, but it does come with several different steps and validation. We categorize the errors into 3 categories. There's no error or minor error and major error. And this is kind of a principle of like, here's the query and how well can this kind of figure answer the query. And if you get different scientific conclusions compared to the ground truth, then it is a major error. We also generate a rationale why a particular error category was chosen. Okay, so how do we use a large language model as a judge? So here we first actually perform human evaluation, and it's really a lot of expertise from the Cosmic AI Institute, where we had expert evaluation of 270 visualization pairs from various models that we compared, and expert weighing, and kind of talked about what kind of error categories and what kind of rationales. What we can then do with this data is to check whether we can develop automatic evaluation with large language models and engineer our context or prompt in a way that it gets very high correlation with the human expert. And this is actually what we did achieve. We had a 80 roughly correlation with the human expert. So we are pretty confident that this is doing a good job. Okay, so just a couple of case studies. So for example, in this task, the visualization you see on the ground truth on the left, and then generated visualization on the right. So this kind of, the globe is kind of shifted a little, but there is not a huge error that you can kind of fix it in a minimal way, and you will be able to get your conclusion. But compared to this is more of a major error, where you have, again, ground truth on the left, generated on the right. And for the generated code, it's really different from the ground truth code, and you'll likely get different conclusions if you look at the generated visualization. So this is a major error. So let's take a look at how models perform. We had, again, 864 tasks. So in blue, this is for processing tasks. And in green, we have visualization task. And you can see the models are they're kind of doing half okay with processing tasks, but when it comes to visualization, the percentage of models getting the visualization correctly is really low. So this is kind of a challenge that we have found with large language models when they perform this sort of scientific visualization for astronomy. Okay. So with that, I want to kind of move to the next topic, which is a thing that is very hard to evaluate, right? Before we have, hey, here is visualization, and here's judgment, how good they are. But I think when we are, in today's era with large language models and how it's impacting science, it's also very important to think about what their fundamental capabilities are. And the one that we tackle is creativity. So what are we looking at, right? So the starting point is that a lot of our discovery, including scientific discovery and other creative applications, is about drawing connections. And this kind of creativity is called associative creativity, the ability to make novel connections on concepts that are, not usually considered connected. And it's part of divergent thinking. Can we brainstorm different hypotheses? Can we brainstorm something new? And we probably want the model to be able to do this for various reasons. But it's really hard to benchmark in a more objective way. So this is what we tackled with the CREATE benchmark. The paper was just archived the day before yesterday, I think. So the create benchmark is about drawing connections between concepts. So the query goes like this. How does Dakota Johnson, an entity, connect it to people who start in another class of entities, fantasy or sci-fi movies? So this is kind of a question that, if you're into trivia, you probably know how to answer. And they may have like very, very creative answers if you're a trivia buff. And this is one of the domains. We have biochemistry as a different domain and so on. So I will kind of not go into this. So let's think about what does a kind of connected network look like. So we start with Dakota Johnson, the root entity. So we know that she is a citizen of the United States, and Elijah Wood is also a citizen of the United States, and Elijah Wood starred in The Lord of the Rings. You can see this is a connection that you can make, although being citizens of the United States is kind of a weak connection, right? On the other hand, Dakota Johnson starred in The Materialists, and Chris Evans also did that, and he also starred in Captain America. Now, this is a much more closer, more specific connection. However, it's probably also typical. It's not super creative compared to this one, Antonio Banderas. He is the stepfather of Dakota Johnson, who starred in Star Trek 2. Right, so, okay, so you can see that we have weak connections like this, and strong and typical connections like this, and also strong, less typical connections like this. So ideally, we want the model, a creative model, to be able to come up with the strong and less typical connections, okay? What we can do with this sort of network is to come up with a metric. So we call this creative utility, where it is a product of both quality and diversity. And we also have a patience. So imagine you're querying the model for an idea. You have some patience of how many outputs that you want to see in the first place. So if you have very little patience, you want the most creative thing right away, compared to if you have a lot of patience, you want to see more and more, and it's okay if the most creative thing comes at number 10. Okay, we looked at how models can answer these kind of queries, and we looked at, we saw something quite interesting. So the models are brainstorming a lot. This is a kind of a snippet for in-domain brainstorming, looking at movies. The models are also brainstorming for atypical connections, like, oh, maybe this is an event that I can connect entities to, or maybe there's a family connection I can connect to. And finally, the models, especially Quen in this case, they are doing some search by listing the possible connections and inspecting each of those. We also observe failure modes, and this is a very common one. The models kind of like started repeating entities, even though they are already shut down by themselves earlier. They're kind of going back to it. And here is how these models turned out to be. We kind of measured 17 models across different families. And there is, so on the y-axis, you see kind of the creative utility that I said earlier, and on the x-axis, it is the patience of the user. So we can see there's a very big gap between the open source models and GPT versus Gemini, where these closed source models are somewhat better at coming up with novel and diverse connections. Okay, so in the last part of this talk, I will allude to, at a very high level, the eval agent framework that we developed. And this is trying to capture, as a user, you may not always know the kind of the domain that you're asking, and therefore you don't really know what kind of criteria there are to actually check what's the whether the output is actually good. So for example, I'm sure nobody here, actually, okay, I myself don't write for New Yorker. Maybe some of you do. But let's say there's a query that is about writing a New Yorker style fiction given this kind of plot. Of course, this does not, it's not just about fiction. You can also imagine other kind of open-ended queries. So how do you evaluate this in a way that is fine-grained and you can actually get improvements once you evaluate and understand where things are wrong? One thing is you could see whether you can derive some criteria from the instruction itself. So for example, if you give this kind of instruction, then the response should look like a New Yorker style fiction piece. It should have the details about the plots and characters, right? So what's wrong with just this? This is about validity of the answer, not the quality of the answer. An answer can satisfy both of these, but still be very bad. You can also prompt a large language model for its parametric knowledge about your task. And if you do that, you see responses like this. The generation should have a coherent structure and flow, and the characters and themes are developing in a way that aligns this kind of genre. But this is also, it's very ambiguous and it's vague. It's very subjective. You almost don't know how to judge it in the first place. So neither of these are actually satisfactory to kind of what a good evaluation metrics should look like. So our idea is if we can synthesize some expert advice from the web, then we can maybe get at higher or better quality evaluation metrics. So eval agent is developed to generate these kind of very implicit but also task-specific criteria by mining the web documents. So the first step we have is a query generator where we decompose the query into more implicit aspects of the task and making them explicit. And for each of these queries, then we retrieve expert advice for instructional documents that we can find on the web. We can then summarize the documents and then convey these into particular criteria. And finally, we can have a criteria generator where we aggregate these kind of checklists and re-rank them so that the model will figure out what is the most important aspects or criteria to evaluate on. So if we come back to this query and think about what makes a good criteria, we're looking for something that is very specific. It tells you a very informative way what is the aspect of quality you're looking at. It needs to be non-obvious because otherwise it's related to like validity and also the things that you already know, so it's kind of not that meaningful. It also needs to be actionable. So if you understand what is going wrong, then you can have either a model or yourself to correct it in a way that's effective. And the previous criteria that I shown earlier, it satisfies none of these three. And what we did show is that eval agent was able to mine criteria like the response should have physical details, environmental interactions, and that reveal character traits. And that is both specific and non-ambiguous. It's also actionable. All right, so I think that's all the parts that I would like to talk about. Overall, I would like to emphasize that evaluation really matters. It's not just understanding the quality of your model, but also it impacts the future development of your model. And what's really highly challenging that has been a consistent theme throughout NLP is the evaluation of open-ended and subjective tasks. And with kind of what we have done, we have tried to tackle this like very multifaceted problem by, I talked about AstroVisBench across different domains and specialty. I talked about Create, which is about something that's hard to like really evaluate. And then eval agent, how do you actually decompose the task into specific criteria? And with that, I will thank my collaborators consisting of computer science folks, philosophers, and also scientists, and all my students as well. Thank you.
Thank you very much. Do we have any questions? Stuff from Eric.
Yeah, really interesting stuff. When I think about the last part in particular, this point about subjective criteria also has embodied in it some sort of probabilistic element. If I ask a friend to look at, something that some AI has generated, and they say it's great, another friend might just say, no, that was terrible. And it's mostly because I hate New Yorker style fiction or whatever.
Yeah.
Have you thought about how to do this in a way that captures, the fact that subjective doesn't just mean subjective, it also means not everybody would agree about what's good?
Yeah, that's a really good point. We actually see that it's a recurring theme. So even for the first part of the talk with Astrophysics Bench, right, we have experts agree on like the gross, larger, more coarse categories, but they actually disagree a lot on how much within those categories things are correct or incorrect. And with these more subjective, like fiction writing, this is definitely the case. What we have tried, let me see, with this pipeline is we do have an aggregator. So the idea is we can have all these different opinions, and instead of saying, hey, this is good or bad, what we can then do is to turn that into a criteria. So maybe you should look at the character development, or maybe you should look at agency, and here is what that should look like from the expert point of view that we mine from the web. So it's at that point, it's not necessarily about judgments from other people, but rather the aspects that people should look at when they judge a particular piece of output. Now, it does mean like, well, once you have your list of criteria, you can still have disagreements among people, and that is not something that eval agent will be able to address. Yeah. Thanks.
One from the back, and then.
Yeah, really awesome work. So there's a lot of discussion now about how benchmarks are getting saturated and the models might even overtrain. And I wonder if there's other ways to test outputs, whether it's AI or myself or one of the developers that writes some code and makes something. There's not always a right or wrong. I mean, sometimes I haven't defined my requirements well enough for the developers. That happens often. And so instead, I'll maybe add some intermediate tests of like, well, did it actually, find the catalog, and let me plot up the data points. And so,
can I ask a clarification question? Please. So like, are you asking how do we know whether it's AI or human, or is this about something else?
I actually care less about that. I think whether it's AI or human, or if it's me or somebody else, that I'm going to add some intermediate tests. It's not like so much of a right or wrong. It'll be more of a like, oh, I got to add some tests and maybe debug a little bit and check whether it's right in some sort of.
Yeah. I think there is definitely a lot of kind of interesting development that we can kind of tackle here. One limitation for Astrophysics Bench is definitely the fact that there is one query and there is no like multi-turn interaction going on. I think some of other so I think other groups in Cosmic AI have been also tackling that. So for example, if you need to open a file and it runs into an error, maybe you should, if you need to parse a CSV file and you run into an error, maybe you should first open the file and see what it looks like, and then do your code. So this kind of more exploration aspect is also something we're working on. We don't, I think in general, it's a much more meaningful problem when you have this sort of more interactive and intermediate checks. And this is also what's happening with, I think, agents, and we can kind of more steering their behavior. Yeah.
One more question?
Sure. Yeah. So this was really interesting. Can you go back to the slide where you were evaluating how good they are for visualization?
Yeah.
So, to give you kind of an example, so, I'm an astronomer, so I had new data coming in from JWST, and I hadn't analyzed JWST data before. So, I go into Claude Code and it kind of say, this is what I want to do. And then, you know, I kind of go and I evaluate it at each step to see if it's doing in Python and other things. So I think this, and, you know, I could do something that would take a week of me reading documentation in a few hours. But I'm wondering, as like astronomers, you know, this is kind of a new way of doing things. And so we need to understand where the failure modes are.
Yeah.
And like your visualization, I feel like it had like a really low percentage in the histogram. It was like a percentile. Is that like minor things where you could correct them, or is it actually giving you totally outputs?
Yeah.
So, I mean, it's interesting for me because, you know, I'm an experienced person.
Yeah.
Data analysis for like 20 years, but
yeah.
a grad student or something.
Let me see if I can actually go to the website, because the green is only about absolutely correct visualizations. But it does not contain those minor errors that you can correct just with one modification. Let me see if I can get, oh yeah, here it is. So this is the website, and so we do have, let me see, this score. Yeah, so this is the minor error percentage, and this is the major error percentage. And you can see the minor error, it's not a small chunk. So the models are doing something. So you could say, you know, maybe a third or to a quarter of the time they're, you know, doing something that you can just correct it with minimal effort. Yeah.
Well, it's still interesting because it's like a new way that we need to do things because it's faster, but also like we don't want to fault, you know.
We have started looking at like what you know, what exactly the models are doing wrong. I think they don't have good priors of what conventions there are in astronomy, and also kind of the estimates that they have are sometimes wrong. So, you know, there's I think the fun one is like sometimes the axis needs to go from large to small instead of small to large, and they don't know. Yeah.
Thank you very much, Jesse, for a very important talk on this topic. And let's thank our speaker again.
Oh, yeah. Forgot about this.
So we'll take 8 minutes. Sure. And then we have 2 minutes for a question.
All set? Okay, great. So I'm going to talk to you about hidden hearts, sharper eyes. Can LLMs classify galaxy morphology better than humans? This is done by myself and my postdoc, Connor Ajay. So sky surveys have really revolutionized what we can do with galaxy morphology. So, you know, surveys like the Sloan Digital Sky Survey had, you know, tens of thousands of galaxies that you could actually do morphology on. Now we're really in the golden era, I think, of galaxy morphologies, because you can see some of the images here. These are actually from Euclid, but we're really talking about millions of morphologies. So one of my scientific interests has been, you know, how do galaxies with growing black holes, which we call AGN, how are they different? So this might be related to mergers and dust lanes and bars. But the exciting thing is Euclid and Roman are basically 20 times better, you know, 10 to 20 times better in spatial resolution than ground-based surveys. So it's really going to give us, you know, and 100 times the field of view of Hubble. So it will give us a really amazing understanding of sort of millions of morphologies. Okay, so those will be great for distant galaxies, but actually for nearby galaxies, Hubble has already shown us that we have these incredibly complex pictures. And because, you know, I'm interested in black holes at the centers of galaxies, you can see things like dust lanes, spirals, merger signatures, star formation. So My focus has been about 500 AGN galaxies that we observed with Hubble. We've had this 5-year GAP program, so it's in the optical and also in the near infrared with adaptive optics. And we're using inactive galaxies, and we set up this Zooniverse classification scheme, which I'll tell you about. The original idea was we would take the label data and then we would use that for the much larger surveys of nearby galaxies, because Euclid is covering a lot of the sky. So, 20,000 to eventually 130,000 nearby galaxies. But this talk, we also, I started kind of looking what LLMs can do because they've improved so much very quickly. So the Zooniverse project, this is myself, and there's a lot of early career scientists, but they're all, astronomy undergrads or graduate students, to give you some background on who did the labeling. So what we're actually interested in is the nuclear morphology. So kind of within a couple of kiloparsec. So this is showing you the Zooniverse labeling scheme. So on the left is the ground-based image. In the middle is the near infrared from adaptive optics or Hubble, and on the right is the optical. And so what users are doing is they're selecting all these different unique features, like is there a nuclear spiral, is there a nuclear ring, is there a bar, is there a hidden merger, things like that. So to evaluate this in the LLM, I used Claude Opus 4, and I input 6 images per galaxy. I should also mention just on this one, so these are just different stretches for the image, sort of in the middle and the right column. So to bring out some of the features for the user. So going back to this, I used Claude Opus and basically did the same classification scheme that the labelers did, and with a confidence interval of 0 to 100. So with labelers, basically what we do is we look at the number of votes and get a percentage. So the sample, again, was just these 32. We could have done a much larger sample, but this is kind of where I started. I didn't realize how easy and quickly it could be done. So to give you an idea of what the human feature prevalence was, so for 32 galaxies, you can see one of the main things that was found was point sources. So a lot of the AGN galaxies have these bright point sources at the center. In addition, there were nuclear dust lanes, nuclear spirals, and some of the more rare features we really didn't have enough in this sample to study. So one of the first things we looked at is the confidence. So this is basically, so if a human said, when we averaged the human votes, we had 70%. And what we found is that the AI tended to have a much higher confidence. So on average for nuclear dust spirals, 23%, nuclear spirals, 21%. And then some of these rare things, a much lower percentage. So the next thing we looked at was to do a rank order correlation. So of the confidences by comparing them. And you can actually see with the Hubble data, we do get very good correlations. Hubble data has the most information in the optical and the most features. So I think that's telling you something really interesting. The other point is that for point sources, actually, with the ground-based and the near-infrared data, there really was no correlation. That's possibly telling us that's something that's hard to measure. Just to give you a few specific examples. So this is a fairly complicated galaxy. It's a bit hard to see, but you can see these sort of black regions right here. So that would be a nuclear dust lane. This, you could say, is a nuclear spiral because you have that dark band coming around here. There's 2 galaxies, so it's a nuclear merger. So actually, the interesting thing is that the LLM found a nuclear dust spiral, which I actually agree with. I don't know why I sort of missed that classification. And I can see also how there could be a nuclear spiral. I could see where it could come up with a point source, although there is not a point source at the center of the galaxy. There's other errors that only an astronomer would know. So this is a saturated image at the center, so you get these dark bands. And the LLM suggested there was a nuclear merger, but I didn't train it to really understand that. So I think there's a lot of interesting things that's found. The other thing is that the LLM I said you can use other categories that we didn't have in our classification scheme. It really wanted to do tidal tails and asymmetries. So it actually did that, and I looked at the 5 cases, and they were actually all good cases that I would agree with. These are associated with mergers. You can kind of see that there's an asymmetry of the emission over on this side. So I have a little bit more time, so I'll just mention, let's see, I wanted to mention one other thing. So we did do a comparison actually with Zubot, which is a convolutional neural network. It's kind of the gold standard, I think, right now. It looked at, 1 million human-labeled galaxies. And so here you can see the nuclear dust lanes. So we trained it, on basically half of our optical samples, so 300 out of 500, and then we tested on 200. And the accuracy was 72%. And surprisingly, our LLMs, I didn't make this up, my postdoc did the Zubot, is 18 out of 25, so 72%. So it is actually interesting that we're getting sort of similar levels of accuracy between the LLM and the CNN. So I think that was surprising. So I'll just leave you with my summary. So there is a strong agreement between the LLMs and humans in terms of the features they find with Hubble. We do see that they can detect faint features that humans miss. I think in general without hallucinating. The other point I think is LLMs are actually helpful at classification design. A lot of the cases where they're finding differences are where there's multiple features. And so you can see a human, if they have to click 4 things, maybe they miss something, it's a little bit more complicated. Maybe they're tired watching TV. It's good at design in terms of suggesting new features. So I didn't realize how quickly this could be done, but basically, it did 32 galaxies with 6 images in about 6 minutes, and it only cost $1.50. So this really is scalable to, right now to thousands of galaxies. So what are our next steps? We're going to expand it to the full sample of AGN and inactive galaxies. We're going to do benchmarks against Zubot, and I think there really is a lot of space for improving morphological studies using LLMs to look at low confidence things. If you're doing multi-wavelength studies, if there are these rare morphologies you didn't think about, or just to do initial labeling for your CNN. So I am an astronomer, and if anyone is interested in joining what we're doing, I have very little expertise in AI, so I'm always helpful to have more people who are interested in this. So thank you so much.
Okay, great, thank you. We have time for maybe one question. Yes.
I wanted to ask something. Where can we see a paradigm shift? As you said, Zubot has been doing this, some other groups have been doing this, you are trying this, but do you see any specific way in which we can do any of these applications where we can see something, as you say, going after the rare ones and so on?
Yeah, I mean, I think Zubot is very good for, gross galaxy morphology. Because, the million galaxies sort of look like that first picture that I showed. But if you're trying to do different types of things, like, the nuclear morphology, which is something new where you don't have a lot of labeled data, I could see a lot of value there. I could also see, comparing LLMs versus CNNs to see how you could improve your accuracy with the human involved. So I think there's actually a lot of usefulness. Certainly that's something we'll look at as we move forward.
But as asking more specifically, do you see any technologies or any combinations of these which could be useful in going in that direction?
Yes, I mean, I think, so there are a few, I think it's like Galaxy Clip, there are a few people who are trying to put these together, CNNs with LLMs, but I think they're kind of still in really development of doing this. But there's going to be tons of morphologies coming out of Euclid in the optical and Roman in the near infrared. So it really is an exciting time. And I think there will be a lot of different designs that combine the two, because I think that is actually better than just using labeled data through a CNN. It allows a lot more flexibility and testing and other things.
Great. Okay, let's thank our speaker again. And our next speaker is going to be Vidushi Sharma, who will speak about LLM analysis of GCN circulars. Okay, so yeah.
Am I audible?
Can you all hear?
Yeah, the lapel mic goes to Zoom, so that's
Okay.
yeah.
Okay.
You have a countdown clock.
Oh, thanks.
Venus gets to
Sorry, I'm not familiar with key. How do you
Yeah, please.
play? Okay.
Yes.
Oh, perfect. Okay, you all
Okay.
Thank you.
Okay, good morning, everyone. I am Vidushi Sharma. I will present our recent work on large language model driven analysis of GCN circulars. So to cover everyone, a brief introduction of GCN, General Coordinate Network. So it is platform facilitated by NASA for distribution of alerts between ground and space-based observatory and thousands of astronomers worldwide. So GCN has been there since 30 years and it has evolved from the community observing gamma ray burst to observing gravitational wave, neutrino detection, and high energy transit. Even new FRB transits are also reported through GCN. So,
Dr. Sharma, can you turn your lapel mic on? Is it on?
yes.
So, yeah.
It's on the top there.
Thank you.
Okay, that's not it. So GCN is a follow-up mechanism for enabling the quick follow-up of transients and the multi-messenger astronomy. So it comes into two products. So one is GCN notices, which is shown on the left side. It is written by machine and read by machine. It is key value pairs, and we recently moved to JSON format. On the right side, GCN circulars example is shown for Fermi GBM. So these are the human written report, and these have free form text and rich in scientific information. So almost every mission has reported their GCN circulars for transients. So we have used large language model for these GCN circular. On the right side, we have this code, open source code over the GitHub for this work. So why large language model for GCN circulars? So on the right side, GCN circulars over the time is shown the evolution, and we can see that it has evolved in terms of number of users, especially after the migration in 2022. So now it has almost doubled the users. And on the left side, human written GCN circular is shown, which has unstructured data format. So it is difficult to be parsed by traditional methods. So with now archive hosts more than 43,000 circulars, and which is increasing rapidly. So the new large language models, new techniques are capable of finding the pattern from the text and extracting the information. So with this purpose, we studied the GCN circular using topic modeling and information extraction. So with this topic modeling, here is the pipeline, what we have used in the paper. So most of the talks have already used these terms, embedding space, contrastive learning. So I will not go into the detail, thanks to the previous speakers. So in the blue color, unsupervised BERT topic is shown, which is used over the circulars. It basically finds the patterns in the archive and find the similar astrophysical topics without manual label. In the red color, the fine-tuned model using the contrastive learning is used. So where we provided the labeled circulars, and they found the similarity between the circulars and the labeled circulars to find the clusters nearby each other. So in the first step, as I mentioned, unsupervised one. So here we use the BERT topic pipeline, and it's the embedded space of circular. So each point here presents the GCN circular text, and each color is different astrophysical topic, and it is clustered over the space. So on the right, the first four most important keywords are taken from each set of circulars. So in that blue color, you can see that GRB, afterglow observations are clustered together, and in the red color here radio observations are clustered together, and we could find the dominant topics such as LIGO Virgo, neutrino detection, swift back GRB detection, Fermi GBM clusters. So with this, after finding the pattern in the archive, we went to the more accurate pipeline. So we used the supervised classification. So our purpose was here to classify the circular based on observations and the messengers. So with this purpose, we fine-tuned the model using 5 topics. So one is optical observation, which is shown in the blue color. So in the embedded space, you can see these are all together. And on the red color, high energy observations are shown. In the green, radio circulars. In the yellow, gravitational wave circular, and in the purple, neutrino observations circulars are shown. So here, interestingly, you find how the community have evolved in multi-messenger domain. So here the GCN circulars over the time is shown, and we can see the optical high energy radio circulars have been there since the beginning, whereas the neutrino and gravitational wave appeared in last 10 years, basically after the first GW detection. So this is something I took the slide, took the idea from the Karthik slide. So he presented 2 days back. I also plotted the similar from the diffusion plot. So it's like a fantasy land inspired clustering diagram. So where high energy observations are your mountains, and blue one are the optical observations sea, and the gravitational waves are the ripples, and the neutrino as the glacier field. So I like this artistic view we can use from the machine learning. So now with this more accurate pipeline, now we want to focus on the type of user. Suppose there are different kind of users in for using the archive, and someone is interested in only gravitational wave cluster and its counterpart. So with this purpose, we fine-tune the model, and the code is available. One can customize it also based on their requirement. So we classified in 3 labels: gravitational wave counterpart, and non-gravitational wave cluster. And the blue one is non-gravitational wave C, green one is LIGO Virgo detected circulars, red one is gravitational wave counterpart circulars. To see the accuracy of this cluster, we also overplotted, manually extracted the 170817, which was followed very regressively for the BNS merger. And we find these yellow points are exactly lying over the gravitational wave counterpart and the gravitational wave event as expected. So we find this is like a good accurate pipeline which can be further used for specific clusters. Here the evolution of GCN circulars over the time is shown to find how it is performing. So the gravitational wave and the gravitational wave counterpart, you can clearly see there are peaks and the increase in circulars in red and green color since 2015, and it increased during O1, O2, O3 and O4 runs. So with this, now I will move to the information extraction, which is another way like LLM can be used to extract the structured data. So for this, we used open source model for research purpose. So we used Mistral, and we provided the GCN circulars to it. And you have heard this RAG pipeline since 2 days, and you're already aware, so I will not go into the details. So first we use the retrieval step. For this, we found the keyword search and the neural search query. And for those interesting circulars, we moved to the generation step where we did the prompt engineering, and we extracted the Redshift JSON file. So we extracted the information Redshift, event name, instrument, and Redshift type, and we find it is accurate with 97% with respect to Swift manual table. So as a last slide, so here we can see on the left side the side-by-side comparison of Redshift is shown, which is predicted versus the manual reported Redshift is and the telescope and the GRB names are given in the table. On the right side, using this database from the circulars, we have plotted the redshift distribution present in the GCN circulars. So here it goes, and thanks for the listening. And we find LLM has potential for this transient alert system and will go from archive to real-time pipeline further.
If we have one quick question, Attila?
Thank you, Vijay. I was wondering how diverse and different are the topics that you find with BERT topic compared to the metadata information we have on top of the circulars. Because we have on top of the circulars, we always have
subject,
a header like subject, where you have keywords like GRB detection or Fermi-Lat observations. And I was wondering, when you mine the text with your different language models, how these topics that you find from the text are different from the headers? Are they similar or?
So we didn't exactly go and check that, but in the similarity matrix we had 80-20 ratio already for test and training, and there we'll find that it has 98% accuracy. So we had already labeled circulars and we tested with that.
Thank you again. Great. Our last presentation is by Mike Smith. Okay. Yes. Just.
Okay. Well, let's clip it on first.
Mike will tell us why text is all you need. And there's the countdown, 20.
Okay, sounds good.
Thank you.
So can you all hear me through this mic? It's all good? Okay. So yeah, I'm going to be talking about how text isn't all you need. And I'm Mike. I'm an AstroScI fellow at the CFA, and I'm also a member of University TBD. And I just want to start by refreshing everyone's memory about what's underlying all of these LLMs, and it's the GPT model. And all these are next token predictors. So it's a stack of decoding transformer layers, and they're trying to predict sequences. So in an LLM, it's a sequence of words, but you could imagine putting in a time series or maybe a sequence of image tokens and trying to predict what comes next. And if you do this for long enough on enough data, you need to learn some pretty intense predictions. So you need to learn about geography if you want to predict the next token in a sentence saying the capital of France is blah, about history if you want to do that. So this is what's underlying everything. But how do we take these models and make them aware of non-text data? And there's really two ways to go about this. You can take an early fusion approach or a late fusion approach. And it is a reason I picked this meme to demonstrate this. Both of these paths, it doesn't really matter which one you take, you end up at the same point, and you turn out to use the same amounts of flops to get there. So just to get everyone on the same page, late fusion is when you train different models along different branches, and you end up in a trunk, an LLM trunk. So you can imagine here the blue dots are imagery tokens, and the green dots are text tokens, or words. And they both go into the model, they go up their different branches, and then they merge later on. And that is late in the network. An early fusion approach enables multimodal interaction as early in the model as possible. So you've got the blue and the green tokens, the imagery and the text tokens going in, and they're merged straight away. So some examples, you've got Lava and Flamingo from a few years ago now, which are late fusion approaches of foundation models. And you've got Chameleon and AIM from Meta and Apple, which are both examples of early fusion approaches. And the reason I picked that meme in the beginning is because it turns out it costs the same amount of flops, the same amount of training compute to get the same performance, whichever approach you choose. So you can see here, this is a paper that came out last year from Apple Labs, Apple Research. And they were trying to see whether early or late fusion approaches, which one's better to go with to get the same validation or to get the same performance. Now, there are still some reasons you might choose an earlier fusion approach or a late fusion approach. With late fusion, you can piggyback off open source world. So you could take a pre-trained LLM, which already has a bunch of flops already spent, and then just imbue multimodal knowledge into it via a method which I'll go into in a second, and a late fusion method. So you don't have to spend as much of your compute budget to make this work as well as an early fusion approach. So yeah, the path is the amount of compute you spend, and it doesn't really matter which path you take. So I'm going to talk a little bit about first a late fusion model in astronomy that we built at University BD, and then an early fusion model that we built at University BD. And then I'll talk a little bit about something a bit stranger that we also did if we have time. So hopefully we have time. So this is a late fusion model that that came out a few years ago. This is Lava. This is a model that takes a clip encoder like Nolan's Astro Search. That's what powers that. And all a clip is a pre-trained contrastive learning approach that aligns text with imagery or another modality. So that's taken, a clip model is taken. That's one path, and the other path is a text tokenizer, just a standard text tokenizer. They're both passed into a language model, which is then fine-tuned with a low-RA approach. And it turns out, if you take a bunch of image caption pairs, fine-tune the model, and then pass in an image it hasn't seen before, it has knowledge of that image, and it can describe what's going on in that image just from the fine-tuning task. So we saw this, and Sharaf, who's a researcher I was working with last year, was like, why don't we do this for astronomy? Why don't we take a bunch of astro imagery, a bunch of astro captions, and try and make an astro lava? And it's what you can imagine. So we took a lot of astro imagery scraped from Astronomy Picture of the Day with permission from European Southern Observatory and from the ESA websites. We took the captions that went along with these, and we trained a astrolava model, a late fusion approach, multimodal approach. And so the dataset is available if you want to download it. We got around 30,000 image caption pairs. It's ready to go on Hugging Face. And like I said, these to generate the captions are taken from the website, and if you want to generate conversations, which is what you need to do to train a lava, you have to pass them into a language model or have a bunch of people do it, but it's much cheaper to get a language model to do this and generate captions or conversations between a hypothetical astrolava model that's talking and a hypothetical human that's also talking, just so it knows how to have a conversation. And then we use these conversations and image captions to fine-tune the astrolava model. And it turns out it does okay. Like, it does a reasonable job at this. To get these cosine similarities, we took the Galaxy Zoo 10 dataset, which is up there, and it's just 10 different galaxy types. You've got disturbed, merging, round smooth, etc. And we took some text descriptions of these, like single word text descriptions, like a merger has 2 galaxies, etc., etc. Embedded them with a sentence embedder. And then we asked each of these models that we tested, Lava and Astrolava, to describe these galaxies in their own words, to caption them, put that into a text embedder, and got the cosine similarity between the different galaxies and the text paragraphs. And that's how we got the cosine similarity. And the paper is on archive. The models are all available on Hugging Face if you want to play around with this as well. So next I'm going to be talking about an early fusion approach, which is AstroPT. So this is a foundation model we also trained. It's a family of GPT-like foundation models. And the pre-training task, like all GPTs, is just predicting the next words or the next information chunk in a sequence. And you can see here's an example of how you would do it. So you would take a galaxy image, split it up into different chunks by, like, maybe you're taking an image patch, 16 by 16 pixel image patch. and just trying to predict or recreate the next 16 by 16 image patch in a sequence there. And because it's a super flexible approach, you can just pass in other modalities after you have the imagery going in. So you could have, if you want to pass in spectra, you just do that in chunks as well and ask the model to recreate each chunk in a sequence. And you might also have some metadata like redshift, etc. You would just, again, a very long sequence, now predict the redshift, now predict the galaxy morphology. So it's a nice flexible approach to foundation models, I think. There are 1 social and 2 technical reasons I decided to go with a GPT. So I don't know if you guys know the bitter lesson, but it supposes that in the limit, compute is all you need. So intuitively, neural architecture shouldn't matter as long as it's appropriate for the task at hand and you have and it scales, and it's good for like the data that you have. The generative loss as well means that we don't need to like enforce our knowledge on a network. So we can just say, predict the next token. We don't have to tell it anything about what we know about physics or what we know about the data set. It's just recreating the data set. So we don't have to tell the model as much. It can just go off and do its own thing. And the thing that I think is key here is that there's a lot of open source work going into GPT style models right now. And we can collectively benefit by contributing to this community, to this like bazaar of researchers all working on this, and learn from them, and they can learn from us maybe about what we can learn about how these models like generate embeddings and what's inside them. And any advances that we make can then be immediately useful for a text GPT and vice versa. The data set is available. There's around 9 million galaxies on Hugging Face again. So this is 2 terabytes of data, I think. So I'll just talk about one thing we did with it. We wanted to see if it follows similar scaling laws to text GPTs. So we took all of these 9 million galaxies, used them to pre-train an AstroPT model, and just see if it followed these scaling laws, and it turns out it does to an extent. So this is with, if you see on the left there, we've got galaxies that are very zoomed out. So this is with those galaxies first, and then I had like an idea like, maybe we want to zoom in a bit. But anyway, we started with those, and we see a saturating log-log scaling plot here, which is what you would also see in a Kaplan 2020, which did the same thing with imagery. It was also saturating log-log scaling plot. With text, because it's a much more complicated data set, it doesn't saturate so early. But the point is, as the model gets larger, it gets better at this task, this reconstruction task. This is AstroPT 2.0 results. When I zoomed in, I actually made the galaxy take up the majority of the frame. It scales past the 100 million parameter saturation point that I did previously. So I managed to train it up to around 800 million parameters, and then I ran out of GPUs. So if anyone wants to give this a go, the data set's there, the model's there. If you have GPUs, please do, and let me know if it works, because I'm very interested in that. So it's not just the pre-training task, there's also downstream tasks as well. And nicely, those also scale with model size. So you can see here we've got a bunch of different emergent properties of the galaxies. You've got magnitude, color, redshift, stellar mass, etc., etc. And what we did is we took the embedding layer of the model. So we took the penultimate layer, chopped off the end, took the embeddings out of the penultimate layer, and used a linear transform to project them, to train a linear model to predict these properties. And again, as the models got bigger, the properties, the embedding was better at predicting these downstream tasks. And one thing I found super interesting here is the stellar mass, you can see in the bottom left there. Suddenly, at a certain model size, it gets knowledge about what to do with stellar mass. And this is something you see in language models as well. So it's quite nice that that transfers over to astronomical data. It's open source, contributions are welcome. There's a Discord channel where we're all hanging out and talking about AstroPT. There's a GitHub. And if you scan that code, you'll go to one of these places. So that's the end of the multimodality section, and I'm going to be talking about something a little bit more out there now, which is the idea that if you train any model on any data, you arrive at a somewhat similar representation. And this is an idea that really came out of the Platonic representation hypothesis. That is from a couple of years ago, an ICLR position paper. And what they said was that if you take a model that's trained on imagery and a model that's trained on text, and you take the embeddings of both of these models and you compare how similar they are, as the models get larger, maybe these embeddings are converging towards something that's more and more similar. So you can imagine, like, you have a bunch of trees and you have a bunch of text descriptions of these trees. If you pass the images of trees into a dyno model and you pass the text descriptions of the trees into a GPT and you get the embeddings, the larger models have more similar embeddings, even though it's a completely different modality. And astronomy is a great test case for this because astronomy is very, very multimodal, as we all know. You've got JWST, you've got HSC, you've got things that are completely different to imagery, you've got spectra and time series, and you can compare all of these things in astronomy to test the PRH. And this is what Kshitij, Sashwat, John and I did last summer. We were just exploring this and seeing how far we could push it. So to do this, we used the Multimodal Universe dataset, which is a collaboration between lots of researchers to build a web-scale dataset of astro information, astro data. That's easy for people to use. There's more than 100 terabytes of data inside it. It's all meant to be nicely cross-matchable so that people can just take it and use it fast. And we took this data and cross-matched it to build up pairs that we could then test the PRH, the Platonic representation hypothesis, with, of the same astro objects as viewed by different instruments. And just as a little aside, we're now taking the MMU and putting on Hugging Face the 100 terabyte data set and trying to make it so you can cross-match on the Hugging Face servers and just stream the data you want. So if anyone's interested in helping out with that, just let me know. So we did a bunch of cross-matches to get the data sets together. This is, again, you can get it online. And we did two tests, really. So we did a cross-modal test, which is where you can take the same astro objects, pass into two different instruments, put those into the two different models, compare the embeddings, and as the two different models get larger, the embeddings should get more similar if the PRH holds. The other thing we did is we took the imagery from the same instrument, passed it into two models of the same family. So say small dyno versus medium dyno, and then medium dyno versus large dyno, and then large dyno versus giant dyno. And as the model pairs in the same family get larger, you should again see an increasing trend because they're converging towards some ideal Platonic space, embedding space. So this is the main figure in the paper. I'll just talk us through it because there's a lot to take in. So you can see on the x-axis, we have the different models we tested. These are different foundation models. You've got AstroPT, ConvNext, DynaV2, VIT, and iJEPA. And the x-axis there is the model size. So each dot on the x-axis is a different size model. On the y-axis, you have the different instruments. So we've got Legacy and JWST, which are imagery. These are JPEG images of the galaxies compared to Hyper Supreme Camp. And then we've got DESI as well, which is a spectra. So we pass that into the spectra encoder from AstroClip, SpecFormer, and we compare that to the Hyper Supreme Camp embeddings from the foundation model on the x-axis. And the thing that I found quite cool here is that we see a trend even for the spectra model. So even though this is a completely different modality, it's not an image, the embeddings seem to get more similar as the foundation model gets larger. And And the other thing that stood out to me is that AstroPT, which has only seen galaxy imagery, it knows about nothing else apart from this, it seems to perform on par with the other foundation models. So maybe we don't need Astro-specific foundation models. Maybe we can get away with taking open source models off the shelf and just using those. We're currently expanding it. So we're going to expand it to more modalities. This is ongoing work right now. More models. We're now testing it on vision language models. I think Quen and Gemma are the ones we're testing it on. And across more metrics. So the mutual k-nearest neighbors, which is what we tested, is a local metric in the embedding space. It doesn't measure the global similarity, just the local similarity. And we want to find out exactly where it breaks down. One thing that was interesting that we found is that it breaks down for small VLM from Hugging Face. This is a vision language model from Hugging Face. And the reason it did that is because they used a different clip method as the models got larger. So the clip is very important to like keep the physical knowledge within the model and do fair comparisons. We're also testing to see if these models are learning a similar like embedding of physics within them. So maybe they're all converging to the same physical knowledge in the same way, and this is something we're currently testing, or we're currently figuring out exactly how we can test what physics knowledge they know and how they represent it. This is, again, ongoing work, but it's super cool. This has turned into quite a big project. So there's a bunch of people working on this because it's like, I'm just excited about it. If you're interested in helping out, come and let me know. And I just have one more slide, and it's just saying, all of these projects, you can join. There's a Discord server with all of them on. We're all hanging out, having fun. So if you're interested, scan this QR code, and yeah, let me know. And I've got plenty of time for questions, I think.
Thank you. All right, great. Plenty of time for questions. Eric, go ahead.
Yeah, interesting thought-provoking stuff. So the connection between the very last thing you said and the sort of first half of your talk. You know, when I think about how I, as a expert astronomer, embed images in my own mind, there isn't as tight of a connection between the actual image and what I think, right? Like, you showed a bunch of examples of what I would have called red galaxies. And I thought about it for a minute, I was like, they're not actually red. And so the text-based model doesn't necessarily not agree with my classification.
Yeah.
But that's about the convergent physics point that you are making at the end. So the real question here is, do you see any differences between the text-based models and the AstroPT style approach? Like, do they do something where the embeddings become more physical as time develops, and would that map onto these kinds of concepts we say out loud incorrectly, in the sense that the text-based model would never call it a red galaxy because it's not red, but we mean something different?
I mean, I can kind of semi-answer your question, I think. So we tested the VLMs, and we found that the physics subspace is a very small part of their entire knowledge. It's very compact. And they've got a lot of other things in the embedding space that are used for other stuff, whereas for AstroPT, it's very spread out. And it's not so compactable as measured by a PCA compression. So you need far more axes to keep the physical space in AstroPT, where you don't need so many in, say, Quen, for example, which I found interesting. I don't know if that answers your question, but maybe you could join and test that out.
Question in front.
Sure, yeah, I'm a large language model researcher at Johns Hopkins. I'm not an astronomer, so I've sneaked in, and I found this absolutely fascinating. I have about 50 comments and questions, so we should definitely hang out and chat later. I have a lot of experience training large language models at this point at the several billion parameter scale, trillions of tokens, and I'm curious. This, by the way, this is exactly the kind of project I've wanted to instigate at APL. Just our space sector is extremely conservative. And so seeing that this is being done outside of the lab, I think would potentially inspire that kind of work. So there's maybe a potential collaboration there. But my question, I guess, if I had to pick one, is just, did you not at the pre-training stage mix in pure text from standard pre-training data sets? And do you not think that might actually improve downstream performance on astronomy tasks?
For AstroPT?
Yeah.
Yeah, we haven't done that yet. So we've tested it on imagery, and then for imagery and spectra from Euclid as well. And the text is on the cards. What I'm trying to do now is get the multimodal universe ready so that we can stream it down and run it on there. And then at that point, I think is when we do another pre-training run with text included and see where we can go.
And if I can just stick one more question in, what architecture are you using for these training runs?
GPT-2.
GPT-2?
Yeah.
Okay. Okay.
Yeah,
like
it needs to get ready.
It's natively multimodal.
Yes.
It's on Hugging Face.
Yes. Yeah. It's on the cards. Yeah.
Ashish? Great talk. One sub-question before my question. You mentioned you use both optical and infrared images. You showed DAISY and JWST. Are those the main data sets that you're using?
For JWST?
No. Which all galaxy images, for instance, are you using for that?
So we're using, for JWST, I think we're using the first band, the middle band, and the final band. I don't remember the names of them because JWST has...
The reason I was asking is that you said that you're comparing many models. I think there may be more purchase if you were to use many different surveys as well. So you know the positions of these galaxies. If you go to low resolution images of the same galaxies and include those as well, I think that is where there'll be much more. And I think using all these different data sets that we have, that is going to be great. So.
Okay, yeah, I'll do that.
Yes, go ahead.
Not really a question, but super great talk, loved it. Only the QR code isn't working for me.
It doesn't work. Oh no.
I'm putting the link in the Discord.
Yes, I'll put it in the Slack. So it's there.
John?
This isn't a well-formulated question, but thanks for bringing a lot of interesting thoughts. So your take on early versus late fusion for multimodality is quite interesting. It's definitely not what I would have intuitively thought. And I think part of that is driven by information retrieval, where I've seen large gains in late interactions when you're trying to sort of fetch out documents, right?
Yeah.
I don't know if you've seen this with Colbert or whatever. And I'm kind of curious, do you have a good intuitive reason for why it seems like these are plateauing out?
Honestly, I'll go back to the plot. No, this paper really surprised me. So I thought early fusion would outperform late fusion quite significantly for the reasons you're saying. And I'm not sure why they found it doesn't. I haven't done a replication study, but yeah, I don't know. I think this is a question for Mustafa.
You mentioned that you were able to predict some of the actual physical parameters. I don't remember if you mentioned this much, but how are you actually able to get those physical parameters? Like you mentioned that you were looking at images and spectra and stuff like that. How are you getting those physical parameters from the actual model itself?
So what we do to extract the model's knowledge of that galaxy is we pass in the galaxy, we go through the model, we take the penultimate layer, so we chop off the end, and that's just like a vector of some length, and then we project that with a linear transform to a single point, and then we train a little linear classifier on the physical properties that we've cross-matched with another survey. And we do that for k equals 10 folds or something, and we take that as the model performance.
You cross-match it, this may be with some other, I may be confusing it with something else, but do you cross-match it with any literature, other values that other astronomers have gotten for those specific galaxies or anything like that?
Yeah, so this is all on the Smith 42 Galaxies data set. We have a bunch of different physical properties cross-matched from other surveys. So we've got Galaxy Zoo, we've got DESI, emergent properties of the galaxies, etc.
How do you deal with any sort of variety that people might get in those certain values? Like if there's any discrepancy in the values that they've gotten in the past? If any astronomers have disagreed on like a value for like the stellar mass or something like that for a given galaxy.
I haven't tested for that. I've been doing a first and 99th percentile cut to get rid of the outliers, and then running over multiple k-folds. I haven't, because there's like 9 million galaxies, I haven't like seen the discrepancies. But that does introduce some noise, I expect. So it's not going to be completely clean. But we get a signal we expect, and these stats seem to be good. So I'm hoping it's okay.
We may have time for 2 more questions. Ashish, go ahead.
I had a comment on John's question about the early fusion, late fusion. I suspect what happens there is that if you have similar dimensionality, then you would take the same answers. But if the dimensionalities are very different, then I suspect that the embeddings that you get are likely to dictate how those are going to work. So for instance, one narrows down something very quickly, whereas the other then latches only onto that embedding. Versus if you are doing it simultaneously, it is together that it's fun. And I think his hand was up. Maybe he had a comment on that. Sorry, I missed your name.
Oh yeah, Sam. I thought your take was interesting as well, and I think it's correct, but it obscures the broader community's takeaway, which was that while the performance of the 2 styles of model do converge at large compute budgets, early fusion is far more efficient at smaller compute budgets.
Yep.
That's the first takeaway. The second takeaway, maybe the biggest takeaway, is that MOE curve over on the right. You see that the ratio between parameters to data for a compute optimal budget actually falls.
Yeah.
The MOE curve, meaning that natively multimodal early fusion MOE models actually need far fewer parameters relative to the amount of data as the compute budget increases. So I think it's a complicated question. But the community's takeaway was late fusion is dead and early fusion is the direction that we're going, simply because late fusion isn't any better and early fusion is better mildly at small parameter counts and smaller data set scales.
Yep. But this is if you're doing a pre-training run, right? If you don't have the compute to do that, maybe you need to take something off the shelf that's already been spent.
And then late fusion is the only way to do that, precisely.
But will it not depend on something like the dimensions? For instance, if you have an image that is 64 by 64, then you have got that many dimensions coming from there. And if you have text that is only, say, 8 parameters that are coming in, right? That will skew that a lot, isn't it?
Yeah, I think that's correct as well. Yeah.
Okay, great. Great conversations. Thanks again, Mike.
Okay.
And now it's time for poster pops, yeah?
Okay. All our posters.
I just want to close the cabinet. You should.
Right, I'm gonna make some announcements
Yes, we
here and be
do.
loud. All right, folks, we've got 6 poster pops coming up. If you are giving a poster pop during this session, please come on over here and line up. And the poster pops will be 1 to 2 minutes each. Alberto, could we get 2 minutes on the timer? And we 5 of them.
The lines.
I think it's 5.
Oh, counting is hard. Okay. We have 5 poster pops for today. And I'm going to go grab a seat and let the 2 of you run those. After the poster pops, I'll give a few logistical items for our next steps.
Okay, great.
Yeah, I have them all pulled up. If you guys want to come down one by one and just give your spiel.
Okay, so order doesn't matter.
Doesn't matter, okay. Yeah.
You know which one is?
Yeah, that one. And then just.
Just you got it over there.
Okay, that's good. Okay. Hi all. My name is Haley Roberts. I work at Zooniverse and with Galaxy Zoo, and it's a really exciting year for Zooniverse. Zooniverse, if you don't know, is a citizen science platform where you can go online and build a project right now if you wanted to run your own citizen science project. we have enabled all kinds of types of research. I mean, we started with Galaxy Zoo, but expanded into digital humanities and ecology and all that. But we've been enabling all kinds of cool machine learning integration on our platform for years at this point. But this was a particularly exciting year for us. I think next week we're going to cross 3 million registered participants. And in October, we're going to cross 1 billion classifications. So we are very excited about the amount of data and the amount of information we have, but we're also stepping very cautiously into the world of LLMs and integrating that with our platform, as volunteers are very nervous and unsure about some of it. So we've also been running tons of ethical AI workshops and getting those conversations started with our volunteers, and these are all things I'd love to talk to you about at my poster, and I'd love to expand to them. I can tell you about early experiments, but what I really want is if you are excited about integrating LLMs ethically and making volunteers, getting them excited about this, and come chat with me, because we're looking for people who are expertise in this and can help us out. Thanks.
Yeah. Next up is Kira.
Hello, my name is Kira McCormick. I'm a master's student in computer science at Johns Hopkins. And this work is motivated by the question, can LLMs actually encode physical properties in their summaries just through text alone? So we did this by creating a data set of 4,000 X-ray sources from the Chandra source catalog. And for each of these sources, we created summaries based on their physical properties using scientific literature, embedded these summaries, and then paired them with physical measurements, so things like hardness ratio, variability index, etc. And so we've had two main findings. So the first was that prompt engineering mattered a lot. By using a more structured, domain-specific prompt, we were able to improve clustering from about 57% for variability index from the baseline, which was pretty cool. And then the second finding was that the LLM was inferring properties and values that it was never explicitly told. So numerical parameters like power law gamma, which were never said in the scientific literature, were being clustered in the same space in the embeddings. And so using sparse autoencoders, we were able to find that these summaries were using semantic concepts like type 2 QSOs or non-thermal emissions, and the LLM was inferring and encoding these properties in the same space. So this kind of proved that the LLM wasn't just using the language and parroting it, but instead actually inferring these relationships. And if you want to learn more, come stop by the poster or check out the paper on arXiv. Thank you.
Where is the mouse? There it is.
You can also switch it to mirror mode, and then you don't.
Oh yeah, I got it. Thank you. Oh, I'm not sure if that's working. Which one is your poster?
Oh, yeah, I guess that's me.
It should mirror from the menu. There we go.
Great.
All right, great. Go ahead, Dan.
All right, thanks so much. I'm Dan. I'm an astronomer here at Space Telescope Science Institute with ESA Aura, and I spend half my time supporting other astronomers using JWST NearSpec. I've been using AI a lot the past few years for all sorts of things, especially coding, and I've made a bunch of apps I can tell you about if you're interested. Here I wanted to mention a few things I've done for NearSpec. So for calibration on the top left, we have all these little micro shutters, and we needed a functional form for the amount of transmission as a function of position within that slit. So Gemini suggested a Gaussian error function. It wrote up all the code, and this worked great. We shipped this with our latest path loss calibrations. Then on the bottom left, for spectral analysis, we wanted to be able to identify the spectra of background sky. They have the same shape, but they might have different amplitudes for reasons. And so ChatGPT suggested some different correlation functions you might use. It coded those up, and that works great. That's in a notebook that we shipped. On the top right there for observation planning, I made this interactive GUI where you can click on any micro shutter in the array and you can see where the spectra will land on your detector. And then on the bottom right, we've just started working on some help with observation review. So I had Claude and Gemini generate a script to go through the APT file and extract some simple things that we can check automatically, like integration times and reference stars for target acquisition. None of these use AI, but I used AI to help accelerate and improve these tools that we're making for the community. And yeah, happy to talk more. Great. Thanks.
So much easier. Okay, perfect.
Young Chen. Okay.
Yeah. So, hello everyone. My name is Yang. I'm from the Oxford Institute for Astronomy. I'm actually a student of EVA, actually sitting right here. So in my poster, I'm actually presenting a very similar work what Mike has already presented. I'm proposing a multimodal framework for geodesy imaging, and that's in specifically low-resolution spectra. So again, I think a lot of discussion has been done in the multimodal AI just a few minutes ago. So I don't need to explain that much. Essentially, we have proposed an architecture to separate as much modality as possible. The philosophy behind this is that we are involved in a nearest pure parallel program. So each field will have very distinct modalities where we have very much missing data. So we want to separate as much imaging and spectrum band as much as possible. So again, this is a late fusion model. And here I have shown you, in my post, I've shown you different results from image encoder and spectrum encoder. For image encoder, again, I've shown you, this is a single band encoder, so I've shown you some morphology classification results. And for spectrum autoencoder, I showed you the reconstruction and the overall statistics. And finally, we have the initial embedding alignment result. Again, this is very initial. And the main differences with this model, with other models like AstroClip or AIO, is that we do not target to that of such large size of either parameter size or data size. For example, here you can see we're using NearCam or nearest data that consists of only about 500K or 0.5 million samples. And for spectrum, it's about around 0.1 million samples. So it's really in a small size, and our main goal is to do galaxy property inference for nearest pure parallel program. So this is not in a big scale, so it's like a mini project we're going on. So if you're interested in please chat with me later. Thank you very much. Great.
Hello everyone, I'm Clara Saldet, and yeah, I'm a physics student at LMU University, and we've heard today that it's not only about text, and the architectures we've talked about, the transformers, they are also applicable to images. And the main objective of my work was to test the quality of generated planetary surfaces. And while I was doing that, I realized, okay, it's not only about testing the quality of the images, but much more about the ways the methods we have to evaluate images overall. And all of them use models as a background to extract the features from the images. And some of them are the models we've talked about in the last couple of days. And yeah, I've tried to look at the embeddings, understand the embedding space better, the differences that the models have, and the effects they have on the metrics. yeah, and if you want to learn more about this, feel free to come over and have a chat.
Okay, and that wraps up the pop-up poster sessions. Is there one more?
Yeah, I think we don't have a lot of You could also check the box sometimes if there's a more recent. Yeah, let's see if.
Where is it?
It's
Come on
gonna
up.
be in
We'll get it.
Okay. And then if you go to oh, there we go. Yeah. Oh, thanks so much.
There we go.
Is it 7?
Yeah. That's the most recent one, I think.
Okay. Let's see.
Okay, I take it back. One last poster. Sorry about that.
No worries. Okay, yeah, I'm Ben. I work with Joel Kastner at the Rochester Institute of Technology. And over the last couple of years, we've developed a VR tool for exploration and analysis of Gaia Data Release 3 data, which renders a three-dimensional point cloud of sources. And you can plot in velocity space, and super useful for studying open clusters and nearby young moving groups. And recently, we've incorporated a small chatbot that allows you to query external databases and enhance the data with a voice integration, so you don't have to leave the tool, which really allows the user to have a seamless experience of exploring data. So if you see an interesting star and you want to know if the star has like an E-Rosetta flux or a flux from any of these listed missions, you can also search from Simbad or MochaDB, which is an open cluster and association catalog. So in this poster, I looked at the membership of the Hyades Open Cluster, compared it to a literature membership, and then used the AI tool to acquire membership from MochaDB. And I compared all three of them in the plot on the right there. And we see good agreement between all three. But yeah, I would love to talk more about this tool if anyone has questions at my poster. So thanks for listening.
Thank you.
Okay, logistics, as promised. For the rest of the day, we have food, conversations, hacking, and informal presentations. So for the next kind of 2.5 hours, the way this is going to play out is we've got a coffee break, we've got time for the hack groups to work and prepare presentations. Please submit your presentations. If you've got slides, please submit those to the box folder before lunch. Then we have lunch. All right. So the next time you really need to be somewhere is back here at 1:10. Please remember that we have this room, which I think is being a little underutilized during the hack times. We also have the Cafe Con, which is being a little underutilized during the cafe or during the hack time. So please feel free to grab any of those spaces. I will post in the general channel the link to where you should upload your slide presentations. Okay. Now, what's going to make me really, really sad is if please don't make me sad, all of the presentations are beautifully polished with no spelling errors, and it's really clear that folks spent the next kind of hour and a half figuring out how to present it in a beautiful package rather than talking and kind of doing the work. So I need at least 1 or 2 people to insert spelling errors into their slides. This is going to be really casual this afternoon, low stress. So please, spend as much of your time as you can hacking rather than polishing and getting it ready. Yeah, Eric, go ahead.
The agenda currently says 1:50 is when we're supposed to be back here. Is that right, or is what you said 1:10?
1:50. The printed agenda has changed because we shuffled around what the morning talks looked like. So the agenda that I'm working off of is the one that Shemaya put on Slack. Is it the same as the one in the hallway? Would you check that for me, Eric? And let me know if that one also says 1:10.
It's also different from the one on the events resources page, which is what I've been.
All right, excellent. Do you mind checking the one in the hallway if that one says one?
Hallway is up to date. The one in the hallway is
Yeah,
up to date, yeah.
I think it is as well. I think
It's 110.
I think it's 110. We're gonna double check just to make sure that the hallway one is the same as what I'm looking at. Yeah, ground truth is hard.
Yeah, group presentation's 110.
The hallway says 110? Okay, good. That was just a little object lesson in typos. So 110 back here.
After lunch, right?
Yeah, and before lunch.
Before lunch. Oh.
I'm sorry, and before lunch, submit your slides. Let me say that in the other way around because it's a little. Please, before lunch, submit your slides to the box folder and be here at 110. Yeah.
Well, question, so if we decide to like, can we give a live demo and not have slides? And if so, there's no, okay.
0 slides, highly encouraged. Yeah.
Can we plug our own computer in for a demo like that?
Yes. I'm looking, yes, okay, I got a thumbs up from the back. Okay, yes. Yes.
How long each presentation or demo should take?
5 minutes with 2 for questions.
Okay.
So you won't be able to tell us everything. Okay. Other questions? Okay, I will get links to the box folder in the general channel on Slack, so you have that information, and I'll also capture all these times in that post as well, so that you have a place to go enjoy.